For those of you who don't know Neemias, he is currently a postdoctoral fellow, a Marie Curie fellow at the University of Bordeaux. Neemias is also one of the Rock Art Research Institute's honorary research fellows. And Neemias has a very interesting background in experimental archaeology, and particularly as it applies to rock art research. And that's what he's going to speak to us about today. So Neemias, thank you very much, and over to you.
Thank you, David. Thank you for the invitation. It's a real pleasure to have the opportunity to talk to you all. And yeah, over the last years, actually, since I did my master's studies, I'm focusing my research on experimental archaeology applied to rock art technology, to different aspects of rock art production, pigments, the tools, and recently to the taxonomy of rock art. My current project is focused on this subject, understanding through experimental archaeology the impact of taxonomic processes on paintings. And the name of this project is TaphArt project. I will not explain much about the TaphArt project today because, as we talked with David, it's just me to focus on published research. So we'll be talking about some previous experiments we did, but all the scientific reasoning behind this research I'll present and these questions I will raise in this presentation are on the basis of what we are doing in the TaphArt project. So let me see now if I can share it now that you solved the problem. Okay, and I share it here. Is it working, David?
Yes, it is.
Okay, good. So what I want to do today, it's more a reflection, it's a discussion on how we have been using rock art, experimental archaeology in rock art research. Because it seems sometimes that there's some confusion in how we are doing this. We all are making some mistakes, and experimental archaeology has a huge potential. It can help to advance a lot the knowledge in our field. But there are some things that we need to improve. And this presentation is more or less a reflection on this. So first thing is we need to have clear is what is experimental archaeology, and experimental archaeology is a research method that enables the testing of hypotheses concerning the formation and of the archaeological record and the production and use of material culture in the past through the development of controlled experiments. Although its origins date back to the 19th century, the consolidation of this methodological approach took place on the 50s, mainly driven by the need for verification mechanisms that extended beyond the direct observation and the mere documentation of the archaeological evidence. In this context, experimental archaeology emerged as a promising alternative, rooted in this principle of uniformitarianism. It facilitated the construction of inferential bridges between actualistic processes and past phenomena, providing a structured framework not only for refining archaeological interpretations, but also for making inferences about human cognition in deep time, as recently highlighted by Professor Lynn Wadley in an excellent publication. So since this beginning of experimental archaeology as a method, rock art researchers have employed experimental archaeology to investigate paintings and engravings across a wide range of chronologies and geographical regions worldwide, with most studies focusing on one or more of these four topics. The four topics I'll mention now. The assessment of the assessment of the technical affordance of mineral pigments in organic or inorganic binders used in the production of different pictorial recipes, the identification of technical gestures and tools employed in the creation of rock art paintings and engravings, the exploration of the level of artistic expertise and the cognitive abilities required to produce complex imagery, and more recently, the investigation of how physical, chemical, and biological processes influence the preservation and detectability of rock art in the archaeological record. The application of this experimental approach on rock art research over the past 7 decades has brought significant advances to the field, greatly enhancing our understanding of prehistoric artistic practices. However, a critical assessment of the literature on this topic reveals that many investigations still exhibit substantial methodological issues that compromise their scientific reliability. One of the most frequent and fundamental problems is the tendency to refer to practical experiences as experiments. This is a serious issue. Therefore, it's important to clarify 2 key points. First, not all attempts at replication can be considered experiments. And second, experimental archaeology should not be confused with experiential archaeology. As I mentioned earlier, experimental archaeology follows a structured and scientific approach. It is aimed at generating knowledge about the past through the testing of hypotheses via controlled and replicable experiments. Experiential archaeology, on the other hand, is mainly concerned with achieving a material result that resembles an archaeological reference. These activities are not designed to test hypotheses, nor they seek to control the technical process involved in producing the final product. So, while such practices may be valuable for skill acquisition or for educational purposes in public outreach, they do not meet the epistemological standards required to generate data capable of supporting robust inferences about the past, or to contribute to advancement of archaeological knowledge. In the context of rock art research, more specifically, this means that simply producing a painting or engraving similar to an image found at an archaeological site, regardless of the artist's level of skill or the degree of visual fidelity between the replica and the original motif, is not enough for the activity to be classified as experimental archaeology. After all, as pointed out by the experimental archaeologist Martin Ehring, equating this kind of activity as a scientific experimentation is like to equating the act of pouring chemicals into a beaker with conducting a chemistry experiment. Beyond this fundamental problem, it is also possible to identify several experimental programs that are developed without clear research questions, making it difficult to assess what exactly is being tested. Another recurring issue is the lack of proper definition of the independent, dependent, and control variables under study, as well as the failure to account for potential confounding factors that may distort the data obtained. In addition, many experiments are implemented without a structured design, and data is often collected without the use of a standardized methodology, which limits the replicability and comparability of the results. Another serious concern is the lack of commitment to the principles of repeatability and reproducibility, both of which are fundamental pillars of experimental science. And finally, it's not uncommon to find studies in which the inferential limits of the experimental data are significantly overlooked, resulting in biased and unwarranted interpretations of the archaeological record. Given all these issues, we may ask, why these misapplications of experimental archaeology still persist even after so many decades of research and debate? In discussing these questions with colleagues from various universities across Europe, Asia, and South America, we came to a shared conclusion. The root of the problem lies in the widespread difficulty to recognize that our experimental archaeology is only the visible tip of an iceberg, one that hides much more than we usually realize or pay attention to. More specifically, we identified 3 interrelated issues that help to explain the persistence of these methodological issues. First, deficiency in scientific training, including limited exposure to epistemology, hypothesis-driven research, and a superficial understanding of the scientific method. Sometimes we consider that, okay, we are archaeologists, we are doing science, but we are not doing science like people in chemistry, on physics. But no, we are doing the same kind of science. So we need to respect and understand the principles of the scientific method. Second, we observe a weak theoretical grounding, reflecting a disconnection between archaeological theory and experimental practice, and in an over-reliance on archaeometric techniques. Of course, we all use archaeometric techniques, we all need to use it, and they are crucial for any experimental research. But archaeometric techniques are not a solution. They are a method, techniques we apply to document our data. They are not the final answer. It's very common to see experiments that are very well documented, that all the cutting edge techniques are applied, but there's a lack of theoretical grounding, and this is very, very important. And the third problem is a limited transparency and self-criticism, particularly a lack of shared protocols and data sets, and an absence of open discussions about methodological limitations we all face when we are developing experiments. But who is responsible for this? So it's always tempting to point fingers at institutions, journals, or even the researchers who came before us. However, the truth is that we are responsible for this. Each of us contribute to the standards and practices of our discipline, whether actively or passively. We are responsible when we design and publish our experimental studies. We are responsible when we supervise students or evaluate projects. And we are responsible when we accept methodological shortcuts simply because that's how it's always been done. But then comes the next question. How can we do better? Well, if we want experimental archaeology to grow and improve, especially in the field of rock art research, then we all need to be part of the change by embracing a culture of rigor, transparency, and constructive criticism. And precisely for this reason, that together with colleagues, or the colleagues I mentioned earlier, we decided to produce a series of publications aimed at contributing to the construction of best practices for the use of experimental archaeology in our field. The first of these papers, which you can see here, is focused on theoretical and methodological principles. It has already been accepted for publication. It will be officially released in September. In addition to that, we are currently finishing a collaborative paper focused on how to design and implement robust experimental protocols, and we hope to have it published before the end of the year. So, aware of these problems we have discussed so far, and based on the work we have been developing, we now turn to the question of what experimental studies in rock art research need in order to be considered scientifically robust. Let's begin with the first and most fundamental element, a structured inferential framework. This is what gives experimental archaeology a scientific foundation. Without it, we are not truly doing experimental research. We are just reproducing things. So everything starts with the research questions, and not a vague or generic question, but one that is anchored in a specific archaeological problem. This is what gives us purpose and direction to the experiment. From there, we need to define our premises, that is, propositions based on prior empirical knowledge that need to be explicit and justifiable, given that they act as the foundation upon which the rest of the experiment is built. Then come the assumptions, which can be defined as conditions we accept as true for the sake of the experiments, but they are very, very important, as the validity of our conclusions depend on how sound and well-defined these assumptions are. For example, if you assume that a specific equipment is efficient to document a degradation process we are trying to understand, but this assumption is not true, the entire experiment is fake. So it's extremely important that we understand all the assumptions we are considering true in the experiment, and these assumptions must be explicit. Finally, we arrive to the hypothesis, which, of course, as you all know, it's a falsifiable proposition that gives the experiment its testable structure. This should be precise, logically derived from the premises and assumptions, and formulated in a way that allows it to be supported or rejected based on the results of the experiments. When this entire structure is clearly defined and internally coherent, it becomes possible to draw meaningful inferences from the experiment, rather than just descriptions and direct analysis. But even the most well-structured inferential framework will fall short if the experiment itself is poorly designed or inconsistently implemented. Therefore, a rigorous experimental protocol is essential for ensuring that the results we obtain are both reliable and meaningful. Here, everything starts with the definition of variables. that should be relevant for the archaeological questions under study and include independent variables, factors which we intentionally manipulate to test whether they produce specific effects, dependent variables, outcomes we measure to observe whether changes occurred as a result of our manipulations, control variables, which we kept constant to avoid unwanted influences on the results, and confounding variables, which are uncontrolled factors that may interfere with our interpretation and should be minimized or neutralized whenever possible. Once that's done, we need to choose a specific experimental design. This means selecting an appropriate framework, such as a full factorial design or a fractional factorial design, that determines how the runs will be conducted and allow us to test the interactions between variables in a structured and replicable way. In this sense, randomization is another critical step, as it helps to minimize systematic bias in ensuring that our experimental conditions are not influenced by external or uncontrolled factors. Then comes systematic replication, which is not the replication I was mentioning in the case of experience. No, it's not just about reproducing things. Systematic replication is not about repeating the same thing several times, but about ensuring statistical reliability. Without replication, we cannot know whether a result is the consequence of change or part of a consistent pattern. And it's actually very, very, very common to find experimental studies based on one single run. So the experimental condition was tested just once. And this is very complicated, and it's against one of the basic principles of experimental archaeology. We need to be sure that the results follow a pattern and they are not the product of chance. So we need to use replication on our experimental designs. In addition, a robust experiment must include a standardized data collection, which is essential to ensure that the results are comparable and not distorted by inconsistencies in how data is recorded and measured. And especially in rock art research, a robust study must seek a balance between internal and external validity. That is, we must combine high controlled experiments, which ensure reliable data and the identification of causal relationships, with others conducted in less controlled but archaeologically realistic contexts. So in some cases, in some studies, people use just systematic experiments when they are trying to understand a specific question, and that can be detached from the archaeological context. Let's see, we are trying to understand the patterns of fracture in a specific lithic raw material, and then you can use a mechanic arm or a robotic arm to map the stones and understand these patterns. But of course, this is an experiment with a high internal validity, because we can have an absolute control of the variables, and we can observe it. We can identify causal effects, causal relationships between the variables involved. But of course, in the archaeological context, the human arm is not like a robotic arm. We have variations. A knapper will never knap exactly the same way 2, 3, 4 times. So we need to combine these high controlled experiments with less controlled experiments, but less controlled but more realistic. And here I emphasize this: less controlled. It's still we are controlling the experiment, but it's not like in a laboratory experiment. But this balance is crucial in experimental archaeology, and especially when we're talking about rock art research. So a third key element for this kind to build a robust experimental study is transparency and open science. Robust experimental research is not just about what we do, but also about how we communicate what we did. It begins with open access, sharing raw data, protocols, and detailed documentation of our procedures. Without access to this information, our work cannot be critically assessed, reused, or improved. following open access, following open science principles is what enables to both reproducibility and replicability. In this case, reproducibility means that other researchers using the same protocol and data can obtain the same results. So it's about the transparency and precision in how the experiment was designed and reported. Replicability, on the other hand, refers to whether similar results can be achieved through new and independent experiments conducted under their comparable conditions, but by different researchers and with different data. This is another huge problem because in many cases, we see experiments, published experiments that is just impossible to reproduce what was done because there's no information, the data are not shared, and again, this is a basic principle of experimental archaeology, and we all need to follow these principles to make it better. The fourth key element is the sequential implementation of experiments. Over the past few years, we have adopted a strategy based on sequential development of pilot, systematic, and replicative experiments. Pilot experiments are small-scale tests designed to evaluate the feasibility of procedures, to become familiar with the behavior of raw materials, to identify possible issues, and to refine techniques or parameters before committing to a full experimental program. Of course, pilots are not about producing published results. They are about making sure the experiment actually works, which is very, very important before we spend a lot of time, energy, and especially money, that we never have a lot of money, but you cannot spend a lot of money in experiments just to discover during the systematic experiments that there's a problem on your design and the experiment does not work. So this is why it's very important. Some people neglect the pilot experiments. They think, oh, it's not needed. Okay, I did 2 trials here and it's done. No, we need to conduct serious pilot experiments to be sure that the entire experimental program works. This is fundamental. So once these procedures are refined through pilot experiments, we can move to systematic experiments, which are conducted under highly controlled conditions with clearly defined variables and a design that allows us to test specific hypotheses. The main goal here is to generate data that are reliable, replicable, and suitable for statistical analysis. Finally, we conduct replicative experiments. These are designed to test whether the patterns identified under controlled conditions still hold when experiments are performed in settings that are approximate real archaeological contexts. In this sense, replicative experiments help to bridge the gap between the lab and the archaeological record. By moving through this stage in a structured and deliberate way, we can gradually increase the realism of our experiments without sacrificing analytical clarity. And in this way, we are able to balance the internal and external validity across the experimental program. Here, the last but very, very, very important element of a robust experimental program is awareness of the inferential limits of what we are doing. It's something we need to recognize. Some people insist in recognizing it, but all experiments, there's no exception. An experiment in archaeology, it's always a simplification of reality. You can imagine that how many variables are affecting the world. We cannot assume that our experiment will capture absolutely all variables involved in a process, or all variables that affected or that are affecting the archaeological record. So an experiment is always a simplification of reality. This is why experimental archaeology is not built to give absolute answers. We are not trying to solve questions with a definite answer to say things were like this. Absolutely, we are absolutely sure. I did my experiments, and these are the results of my experiments, and this is the final answer. This is not the goal. we are talking about probabilities. Experimental archaeology helps us to understand what is the most probable scenario. If we have many options, in terms of probability, experimental archaeology will help us to support this or that possibility. And of course, we need to recognize and to acknowledge the possibility of equifinality. In the same way, we are trying always working with a simplification of reality. We are working with several variables, but it's impossible to capture all variables. And there's always a possibility that the same results could be obtained through different processes. So we need to be humble in this aspect and be aware that we are working with probabilities and not with final solutions. So to more or less explain in practice how we have been using this, I will show you. Of course, here is it's a simplified version of a study of some studies we have been doing. We applied these procedures to and this reasoning to study the production of engravings in the Tagus Valley in Portugal, understanding the relation between the engravings and the LITC instruments, the LITC tools in the area, and also the relation with the raw materials available. We use this to understand the production of Levantine rock art. Now we are also developing a systematic experiment about the production of portable art in Patagonia. But here I'll show you, briefly show you a case study that was centered on the tools used in the production of Levantine rock art. This research started with my PhD thesis, and after this we published an article in archaeometry centered on the production of pigments and binders, focused on the pictorial recipes. And this experimental program, the other part of the experimental program, was focused on the tools, on the paint application tools used to create Levantine rock art. So this brief example, that's of course simplified here, is to show you the application of this structure in practice. So for those of you who does not know Levantine rock art, it's an amazing rock art located in the Mediterranean area of the Iberian Peninsula. In some senses, it's quite similar to the rock art in South Africa. Images with a lot of movement in some cases, produced with fine lines, very, very full of details. You can see, for example, this figure with the nose, the facial traits of this figure. We are talking about a millimetric scale. The nose of this figure has less than 1 millimeter, for you to have an idea. There's a high precision in everything that was done by the painters. And we are talking about more than 1,000 sites with Levantine rock art. And the sites are spread from the Pyrenees to the south of the peninsula. And for many decades, actually for more than a century, people defended the idea that the entire Levantine rock art was done using feathers. And there's a lot of publications mentioning Levantine rock art as the art of the feather, because according to many researchers, all paintings, no exception, were done using feathers. But when we look at these images, we can see a lot of variability, and we are not convinced that this was the case. So we designed the experimental program to explore this issue, And then we stated these research questions: what paint application tools were used to produce Levantine rock art paintings in the Strasbourg region and surroundings? And why this region? Because this region is is an area considered one of the core area of Levantine rock art. And then several researchers consider that this rock art tradition expanded from from this area. So we selected 9 sites in the Maestrazgo to take as a reference and a sample of more than 1,000 images. So based on research questions, we are basing ourselves on several premises that, of course, I cannot list everything here, but for example, that we are based on the premise that morphological features of painted lines, for example, the edges, the thickness, the internal structure, can retain information about the tools used in their production. This is something that is empirically demonstrated. So we can base our questions and our hypotheses on this. But also, we are based on assumptions that for example, the taphonomic process have not altered the original morphology of the lines, and that the analyzed sample is sufficiently representative of the technology employed by the prehistoric painters. Articulating these premises, assumptions, and the research questions, we elaborated the hypothesis that 2 kits composed of hairbrushes, plant brushes, and feathers were used to produce Levantine rock art paintings in the Maestrazgo region and surroundings. But how to test this hypothesis? So we decided to test 60 different paint application tools with different active zones, pointed active zones, flat active zones, and convex active zones. So we started with defining specific variables, and as independent variables, we selected 2 categories, 2 raw materials, and the morphology of the active zone. As dependent variables, we defined precision, adaptability to the supersurface, and paint load capacity. As control variables, we decided to use the support surface, the paint recipe, and the experimenter. And we identified 2 potential confounding variables: the experimenter technical skill and fatigue. So we took specific measures to control it. For example, to be sure that the technical skill of the experimenter was not influencing on it, we asked for a professional painter with 60 years of experience to test all the tools before the experiment, together with the official experimenter, to be sure that the result was exactly the same when used by the experiment, when used by a professional painter. So in this way, we started experiments only when both the professional painter and the experimenter obtained the same result using each of the 60 tools. Also, to avoid the influence of fatigue, you can imagine we took 6 months doing this experiment, and after several hours painting, it's normal that some gestures will change. So we always conducted experiments under the same conditions to avoid the influence of fatigue in this process. And then we decided to produce straight lines and curved lines, 600 lines in total, to understand the behavior of the tools. And why not just paint images? Because painting full-size images, it's complicated, because it's difficult to understand, to measure outcomes, because there's too many variables affecting the outcome at the same time. So this is why we decided to use lines that are the base of Levantine paintings. All paintings, all images in Levantine rock art were created using lines, straight lines or curved lines. And this way we have an analytical criteria, independent analytical criteria, to properly understand the behavior of each tool. So we developed the experimental design based on a sequential approach with pilot experiments in which we tried everything. We built the tools, for example, the tools were built with 8 different types of hair or from animals that whose evidence was found on their ecological context. We used 6 types of plants, with fibrous plants, woody plants, and spongy plants. So we have a varied set of tools. Using this sequential approach, we decided to produce always 5 lines with which tool. Why? Because replication is important, and we need to be sure that, oh, I painted 1 line and this is the result of the experiment. And we clearly see that this is not the case. There are variations, and we need to produce several lines in this case to understand what was the pattern or generated by this experiment. So replication was crucial, and we used this, in this case, 5 lines. And why we decided 5? Because in the pilot experiments, we observed that with 5 lines, we can capture the variability, the inner variability of an experimental tool. So this is why, again, pilot experiments are important, because it's when we decide, we calibrate the parameters we use in the systematic experiments. Also, we have a very detailed data collection protocol with specific measurements for each lines, in which we'll detail it, how each line would be measured, using which parameters, in which sections of the line. Also, we used macrophotography, microphotography to have all the details of the images of the lines, and to be sure that we could make a precise characterization of the performance and efficiency of each tool. And of course, using this approach based on pilot, systematic, and replicative experiments, in which we painted full-size replicas, we found this balance between internal validity and external validity, because in this part in which we observed the lines and we develop an efficiency index for each tool, we are talking about internal validity. Everything is controlled. We can understand, okay, here we can see that hairbrushes tend to present this kind of behavior, that when the feathers, we use feathers, they have a difficult to adapt to the irregularities of the support. So we control everything, and we know everything which is happening, when we can quantify this. So this is about internal validity. And in the next step, where we painted the full-size replicas, we were talking about this external validity, because the replica is an approximation of the archaeological reality. But still, on this part of on the systematic part, we managed this systematic approach, focus on the high control of the variables, allowed us to establish this efficiency index for each tool, and for straight and curved lines, and allowed us to understand which category of tools were more efficient, which ones were less efficient, and understand what is the influence, what is influencing the results. Oh, is the technical gesture? No. Is the raw material? No. Is the morphology of the active zone? It is impossible to do this when we just replicate, when we just do a replica of a rock art image. We need to use this systematic approach, this analytical part, to understand these causal relationships and understand what is actually happening. So, for example, as a result of the systematic experiments, we managed to obtain an efficiency classification. And also, we observed that, for example, out of 60 tools, only 4 afforded the production of both straight and curved lines. Because, for example, when you use, if you use a tool made with boar hair, it's great for doing straight lines, but it's terrible for doing curves, because the hair is too hard and it's terrible. The hairs or the bristles open during the curve, and you have a lot of errors in the lines. So we also observed that a low or even non-existing correlation between the morphology of the tool's active zone and the morphology of the line tips. This is also a huge myth in rock art research. People usually consider that, okay, if the end of this line here is pointed, this is because the tool used was pointed. But there's actually a myth, because we analyzed 1,200 line tips, and we observed no correlation between the morphology of the tools and the morphology of the line tips. The morphology of the line tip is actually influenced by the technical gesture and not by the tool. So also we observed that what the great contribution of this part was also to give us analytical parameters with independent validation to analyze the real rock art, to analyze the archaeological images. And based on this comparison, that we after we obtained these results, after we classified everything on a systematic way, we managed to establish a comparison between all the experimental lines, the 600 experimental lines, and around 1,000 paintings with high rates of conservation, to understand which ones were actually similar or not to the archaeological images. And based on this, we established a similarity index that allowed us to understand which tools were efficient and similar, or which tools were efficient but not similar, and we can have a general view of the results. And actually, at the end of the experiments, we noted that out of 60 tools, only 5 hair brushes, 3 plant brushes, and 2 feather brushes afforded the production of images similar to those of with characteristics similar to the archaeological paintings. After understanding all these details, then we moved to replication. Then we decided to produce several. Here is just a small sample, but we produced several, almost 20 replicas, full-size replicas of Levantine paintings, to understand other aspects. Here we are not trying to understand causal relationships. Here we are trying to see if this classification is still valid under archaeological conditions or conditions similar to the archaeological context, and to explore other aspects of rock art production. So producing these replicas, these full-size replicas, it was possible to validate the efficiency classification. We observed that, okay, these tools are actually the most efficient to produce this kind of image. And also what was possible to do a functional differentiation. For example, observed that the best use for hair brushes is to do precise outlines, the plant brushes to infill large surface areas, and feather brushes to paint fine anatomical elements. This was not possible during the systematic experiments, but it is possible here because we are exploring other dimensions of rock art production. Also, in this part of the program, we are painting an entire image, and some of them are quite big. So we were able to understand, for example, wear patterns, and to observe that you can use and reuse a brush made from animal hair several times. But we also observed that, for example, brushes made from plants tend to be destroyed in a few minutes, that we need more raw material, for example. And we also observed that these plant brushes, you cannot recycle this kind of tool. But in the case of hair brushes, it's easy to change the bristles and keep the handle, and you have a new tool easily. Also, it was possible to understand, to have insights into labor investment. For example, understand if the images with a lot of anatomical details, how much energy, how much time you need, depending on your level of skill. So it gives us a lot of important information about these other aspects that are not necessarily systematic, analytical, but they are very important to understand more, let's say, an anthropological dimension of rock art production. Based on all this data, on this quantitative data, we obtained it. As I mentioned, this presentation is a very, very simplified version of what we did, but you can see all the information on the article. Based on all this quantitative and qualitative data, we were able to elaborate several inferences about or case study. For example, we were able to say that Levantine painters used a technically sophisticated toolkit, and not only feathers. We observed that feathers it's not possible to use feathers to produce most of Levantine rock art. Feathers were actually used for very precise things, but it's not possible to paint several of the images using only feathers. We also concluded that this pictorial technology did not follow an economicist logic, because the Levantine painters clearly did not choose the easiest way or the most economic way. No, they use it in some cases a combination of tools, a combination of resources that were more expensive in terms of labor investment. Also, we observed this. We were able to say that the priority here was not to achieve, was not just to produce an image, but to achieve specific technical visual qualities. So not only paint is not only about to produce the image of a deer on the wall. This deer needs to have specific techno-visual qualities that are obtained using specific technological processes and specific tools in this case. And also, we inferred that the chain opératoire was likely transmitted across generations because, as I mentioned before, we are talking about 1,000 sites in a large area, and there's an impressive similarity in the way Levantine rock art was produced. So to finish, I don't want to talk about conclusions because this is more a reflection. It's a discussion, it's a reflection, but I want to talk about what we have learned so far. And in 15 years doing experiments on engravings, on paintings, on technology, on taphonomy, we learned that the scientific method is more than procedures, and theoretical grounding is essential for meaningful experimentation. Now, during the TaphArt project, we are working with colleagues from the German Aerospace Center, for example, and they have a very different perspective, and because it's much more centered on the technical procedures, and it's challenging always is to establish these connections, but it's crucial. It's crucial for us to have theoretical grounding, even when people think we are doing just a technical procedure. This is important. We cannot forget that method without theory is nothing. A second point is that, again, I will insist on this. An experiment is different from an experience, just as experimental archaeology differs from experiential archaeology. The third point is that experimental archaeology is hard. And if it feels easy, something is probably wrong. After many years on this, I can say that I never conducted an experiment, and I know that all my colleagues working on this is the same for them. Then we never conduct an experiment to say, okay, it was easy, it was fast. No, this is always hard, is always complex. We need collaboration between colleagues. It's difficult to articulate all questions, all the theoretical dimension, all the methodological dimension, and to obtain solid results. So it is hard. Because it is hard, failure is information and a necessary step towards robust experimental research. We will fail, and this is why we have to do pilot experiments. We will fail several times. We need to build an experimental protocol. We need to adjust it. We need to do it again. We will fail again. It will not work, and we need to adjust and improve until we have a solid and robust experimental protocol that will definitely work. To do this, we need collaboration. Progress in this field requires collaboration because solid knowledge emerges through shared effort. It's impossible to make experimental archaeology better in rock art research if we do not start to collaborate, if we do not start to apply self-criticism, if you do not use this constructive criticism, and if you do not discuss our methodological limitations. We need to collaborate. We need to put these ideas on the table and look at it and try to solve the problems that affect all of us. This way, we can make experimental archaeology better. And finally, as I was telling in the title of this presentation, replication, the act of producing a nice rock art image, as you can see here on the slide, it's crucial, but it is definitely not enough on its own. If we just replicate, we are losing a lot of information. If we can make beautiful replicas, but just replicating, we are not understanding the prehistoric artistic practices, and this should be our main goal. Thank you.